In this video, we're going to look at how we can multiply together floating point numbers. Now, I already have a full course on floating point multiplication, which focuses on 32-bit floating point numbers. Now, this course is about 8 or 10 hours long, and there's a lot of detail and a lot of information in it. So if you're interested to getting into the nitty-gritty detail of the floating point multiplication method, then you can get it in that course. What we're going to have here is a shorter video and just a single video to give you an overview of how the circuit works. So let's start off with an example of multiplying together two numbers which are written in exponent form. So for example, we could have the number 5 times 10 to the 2, and we want to multiply it with 3 times 10 to the 3. Now this is kind of what it's like in floating point numbers. We're going to have in a floating point number the mantissa, which in effect would be this value 5. We're going to have the base. Now the base in the floating point number is the value of 2, not 10. And the exponent is this value here, 2. So we have a base, a mantissa and an exponent. So this is how our floating point numbers work. So we'll just use this simple example here with base 10. When we multiply these two together, well, 5 times 10 squared is the same as saying 5 times 100. 3 times 10 cubed is the same as saying 3 times 1000. So that's the same as saying 500 times 3000. So when we multiply 500 and 3000, we get this number here, which is 15 times 10 to the power of 5. So you can see here then, in order to multiply these together, what we have to do is we have to multiply the mantissa. So the 5 times the 3 will give us the 15, and we have to add the exponent. So the 2 plus the 3 will give us 5. And then we can rewrite this in a normalised form. Now by a normalised form we mean just one digit after to the left of the decimal point. So the decimal point would be sitting here, and we need to have just one digit. So it has to be rewritten as 1.5 times 10 to the power of 6. So you can see here, in order to multiply two floating point numbers together, we multiply together the mantissa and we add the exponents, and we also might have to form this little bit of a normalization. But what's going to happen to the value of the sign? So we have to be careful when we multiply two numbers together, the sign can change. So a plus times a plus gives us a positive number. A minus number times a minus number gives us a positive number. But if you have a mixture of plus and minus, then we always end up with a minus number. So in effect we've got this little truth table here. And this is the truth table for an exclusive OR. So in order to deal with the sign of the final value, we just need to exclusive OR the signs of both the inputs, and we will get the output will tell us the exclusive OR will tell us the sign of the multiplied output. So this is the basic idea. We use the exclusive OR to give us the sign of the result. We multiply the mantissas together. We add the exponents, and we may have to do a normalization. So let's have a look and we'll see the overall circuit that's going to do this for us. So this is the multiplier circuit here. Now I won't get into minute detail on how this works. If you're interested in all of the details, then the best thing to do is to take the floating point multiplier course. So we're going to have two numbers, x and y, and we want to multiply them together. And the output at the bottom here will be x times y. So we have to split both numbers up into the sign, the exponent and the mantissa. So we do that in this block here and in this block. And that gives us access to the sign and exponent and mantissa for both x and y. Now this is split into three sections. The first thing we'll have to deal with is the sign, and then we're going to have to deal with the exponent, and then we're going to have to deal with the mantissa. Now we said for the sign what we have to do is take the sign of the values x and y and exclusive OR them, and this will give us the sign of the output. So that's what we've done here. So that's relatively straightforward. Now we also mentioned that we have to add the exponents. So the exponent addition occurs in this section. We have to multiply the mantissa, and the multiplication of the mantissa occurs here in this section. Now we're also going to have to add in some rounding circuitry, but we're not going to go over the rounding circuitry in this course, but we're going to have something that we can call a sticky bit, and there's a rounding and also there's this increment section, and this here will give us the necessary rounding for the circuit. So the only thing we need to note here in this is that the value here for large EX and large MX, okay, so these, the large EX and the large EY, so these are the exponent values. Those are the biased exponent values, okay, so we've already added the value of 15 on, so these are the actual values that you would get in your floating point number. But what we want to do first of all is we want to subtract off so we can get this small EX and small EY. So this small EX and small EY are the unbiased exponents. So we've subtracted the value of 15 off. We're going to add them together, and then we're going to take a copy of the output into this adder and this adder. And we're going to add the bias back on here and the bias back on here. But this one is a special one. We're going to add the bias plus a value of 1. So it means that when we come down here, we're going to have a choice of two exponent values. There's going to be an EX plus EY plus a bias, and an EX plus EY plus a bias plus 1. Now, when we get down here, we make a choice between these two, and this will give us the final exponent output. And this comes from this OR gate here. And the OR gate control comes from the multiplier in here of the mantissas. Now, whenever we multiply together the mantissas, we're going to potentially, the very last two bits that we multiply together could be a 1 and a 1. So if we multiply the 1 and 1 together, we would get a value of 0, and we would have to carry 1 out into the next position. So that means we're going to have an extra bit on the left hand side. But not only that, up here as well, whenever we do the multiplication, before we do it, we actually add on the hidden bit. So this is the 1 plus m. So when we add on this hidden bit, we're going to have another bit to the left hand side. So we could potentially multiply these two together, but we're going to have another 2 extra bits on the left hand side. Now we may only have 1 extra bit, but we could potentially have 2. And we know that in order to normalise the numbers, we only want 1 bit on the left hand side of the decimal point. So it means that the decimal point will potentially have to float by 1 value, or it might not. So that's really what happens here. The OR here determines whether this exponent has to float by 1 bit or not float by 1 bit. And that's what this extra bit of circuitry does and this choice does. And that comes from the 2 highest bits of the multiplication of the mantissa. Now, whenever we multiply this out, we're also going to have to go through the process of doing the rounding, and the rounding is done at this point here. So we might have to adjust the mantissa slightly depending on the rounding, and this comes through this increment section here. But finally we're going to be left with the mantissa, which is here, and we've got to concatenate each of these 3 back together and give us our x and y. Now that's a short description of sorts about how the multiplier works. If you want to get all the details, you need to go and do the multiplier course, but it's not absolutely necessary to understand how the multiplier works in order to continue doing the Design a CPU 4 course. But if you want to break this down and make it as simple as we can, we exclusive OR to get the sign. We add the exponents and an extra factor of 1 potentially, and then we multiply together the mantissa in order to get the final output here for the mantissa. Then we concatenate it together, and this will give us our x times y. So let's go ahead and we'll have a look at this in the actual Logisim circuit. So let's drop down into the computer and then down into the CPU, and finally we can go into the floating point unit. So from the floating point unit you can see we're interested in the floating point multiplier, and that's the multiplier here. It's got an x and a y input, and it's going to have x times y output. Now we aren't interested in these special conditions at the moment, so we can just drop down into the floating point multiplier. So this is the top level for the multiplier. We've just got an input x and y, and we've got the output x times y. So again we can drop down in here, and I'll make this a little bit bigger. So you can see here we've got the same circuit set up that we've seen in the schematic. So we've got the x and y coming in. We're going to split the x and the y into the sign, the exponent and the mantissa. The sign bits go into an exclusive OR, and the exclusive OR will tell us the sign of the output. We've got the exponent values here, so the exponent values come in here, and we at this point here we are subtracting off the bias to give us the unbiased values, and then we're going to do the addition, and we split this into 2, and we then add the bias back on, and the one on the left hand side is just the bias, and the one on the right hand side is the bias plus 1. And again we've got the choice of these exponents. So one of these exponents, the one on the right hand side, will be 1 larger than the one on the left hand side. And we make this choice. So the choice here comes from this, and it says 22. So the choice is actually coming from the most significant bits of the multiplication of the mantissa, just as we've seen in the schematic. So we make a choice here, and whenever we choose this, we get the summed exponent value. And again here, we're going to have the x and y mantissa, and we're going to add on the extra bit at the top, which is the hidden bit. So this in effect is the 1 plus m. So this gets added on at the top, and we'll do the multiplication. Now there's an extra bit of circuitry which we never showed in the diagram, so it's a shifter, because this mantissa would potentially have to shift the decimal point. Now we're also going to have the sticky bit, the rounding bit, and the incrementer here. And the final output for the mantissa comes from this point. And then we end up with the final output x times y. So there's a bit of extra circuitry in here as well, where we deal with all of the special cases. So there is quite a lot of detail in this. If you think about all of the different special cases you have about multiplying, say, zeros together, or multiplying infinity with 0 and 0 with infinity, and lots of there's not a number as well. You can add that into the mix, so it gets it can get relatively complicated. So we have to generate a little circuit up here for the special cases, and that's what this is. And then there's another circuit here which looks at the types of numbers. So the only numbers we've talked about so far are normal numbers. So in effect we're multiplying a normal number and a normal number to get a normal number. But we could look at multiplying subnormal numbers. So we could do normal times subnormal, or subnormal times subnormal. And we would act on the circuit slightly differently depending on each of those. So that's what this does here. So that's the overall circuit, but it still just works in the same way, the basic way. The sign is determined by the exclusive OR. The exponent is defined by the addition, and the mantissa is defined by the multiplication. So I don't really want to spend a lot of time getting into these circuits. You can get in and have a look yourself, and you can see exactly how these circuits have been generated. But for us in this course, if we can get a brief overview of how it works from this top level, that's all we really need to know. So on the next video, we will look at the adder and subtractor. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.